Good afternoon, students. Today I will continue my discussion on confirmation analysis of cyclohexane. So, in the next part, let us discuss about the stability. Stability of the four conformations which are obtained for the cyclohexane. This is the decreasing order of the stability of the four conformation. So, among these four conformation, the most stable conformation is the chair conformation, and half chair conformation is the least stable or less stable conformation. So in between, when compared to chair conformation, the next stable conformation is the twist boat conformation. Next to that is, when compared to twist boat and boat, boat conformation is less stable. When compared to boat and half chair conformation, boat conformation is the most stable one. And among all, the least or the less stable conformation is half chair conformation, and the most stable one is the chair conformation. So now next part. Here, this is the explanation we can give for the stability, and the factors which contribute for the instability of the conformations are, the first one is the bond distortion strain. These are the various strains which are observed, and they are the main factors which contribute for instability of the conformation. Bond distortion strain, charge repulsion strain, bond opposition strain, and steric strain. So I think we have discussed about the steric strain while giving the stability for the the ethane conformation analysis of ethane. So in cyclohexane, due to the puckering of ring and uncharged nature bond opposition and charge repulsion strain are irrelevant, and here the main internal strain contribute for the strain in carbon hydrogen bond is the bond opposition strain and the steric strain, whereas these different conformations of carbon hydrogen differ in the internal strain and hence in PE content. So what is this PE content, we shall see later. Here, if we go on for the discussion for the stability of conformation one by one, first one is a chair conformation, wherein we observe the minimum bond opposition and steric strain, and here all carbon hydrogen bonds are perfectly staggered. This is the Newman projection formula for cyclohexane for chair conformation. So you can see all carbon hydrogen bonds are perfectly staggered. If you look into the structure, you can see this one. So due to this, we can say the bond opposition strain is minimum in this case. Okay, and whereas the hydrogen atoms on the adjacent carbon atoms have enough space for their accommodation. So you can see in the Newman projection formula, wherein the hydrogen atoms on the adjacent carbon atoms, they have enough space one from the another. So you can say here the van der Waals force is 2.5 angstrom, whereas A dash and E dash for hydrogen atoms on adjacent carbon atoms are separated by 2.3 angstrom unit, which shows this is A for axial, E for equatorial. So the first one is for this is the common, the sum of the van der Waals distance is 2.5 angstrom unit, whereas the hydrogen atoms on the adjacent carbon are separated by 2.3 angstrom unit for axial as well as equatorial hydrogens. So which shows the minimum steric strain, and therefore what we can say is the PE content of the chair conformation is minimum. So this leads to the more stability, and hence we tell it is the most stable conformation among 4 different conformations of cyclohexane. This you can note it down for 2 marks, and this you can write answer, and you can show this is the representation of the chair conformation. And if you take twist or skew boat conformation, we can see here the less torsional strain as compared to boat conformation. Less torsional strain, that is the flagpole hydrogen are far away from each other, whereas C2, C3, C5 and C6 become non-polar. You can just see the flagpole hydrogens, they are far from each other, and C2, C3, C5 and C6, and they are become non-polar, non-planar. They become non-planar due to the twist of the bond. So the energy content is 6.696 kilojoules less than the boat, but 23.02 kilojoules more than the chair. It is more than the chair and less than the boat conformation. Hence we can tell this is more stable than the boat conformation but less stable than the chair conformation. And here half chair it suffers more from the angle strain, and I think already we have discussed about the angle strain in the last class, and it has a 46.04 kilojoules more energy than the chair conformation, and maximum energy content than any other conformation. Hence it is the least stable conformation among all. So why this half chair is least stable? It is due to the maximum energy or more energy which is associated with this conformation. Okay. So this is the profile of an energy profile diagram. We can see for all the 4, and you can just answer for drag the answer for this. For the boat conformation it is 29.7 kilojoules per mole. For twist boat it is 23.02 kilojoules per mole. For half chair it is 46.04 kilojoules per mole. So this is how we can give the stability based on the energy diagram. In this case, on the less stable, more stable conformation part, this is the chair conformation which you can see, and the less stability part, it is the half chair conformation, just you can see. In between we have the 2, that is twist boat as well as boat conformation. This you can see it here, twist boat and boat conformation. This is twist boat and this is twist boat. Okay, this is how you can show it by energy profile diagram. And as we can see, there will be locking of the conformation, that is in substituted cyclohexane, a small substituent which may acquire either axial or equatorial position. With the increase in the size of the substituent, what we can see, especially at 1,3 position, 1,3 diaxial interaction become very severe, increasing the internal potential energy, thereby the stability is decreased. So this is the one example. Very large substituent like tertiary butyl prefer to lie in the equatorial position only to avoid 1,3 diaxial interaction. The existence is the only one conformation is termed as the locking of conformation. So by placing the substituent at various positions, especially if you take the example of 1-3 positions, 1-3 diaxial positions of the conformation with various substituents. It is example of small substituent as well as with a large substituent. Both the cases we can see. In case of small substituent, the interactions will lead to the increase in the internal and potential energy, thereby the stability of the conformation is decreased, whereas the large substituent, say for example tertiary butyl, in the equatorial position, they avoid the interactions and making the conformation more stable. This is how we can talk about the locking of the conformation. With this, I think we have completed the first aspect of the conformational analysis of cyclohexane. Thank you.